product starts with two vectors and outputs another vector, and that third vector is perpendicular to both of them, and its magnitude depends on the magnitude of the two vectors. So to understand what that means, again, we'll start with the sort of a geometric view. Set up our x, y, and z axes here, and we have our unit vectors in each of the coordinate directions, so I, j, and k. And without losing any generality, we'll just assume that our a and b vectors happen to be in the xy plane. It'll just make it easier to draw, but the understanding will be the same. So let's imagine a vector goes somewhere over here in the xy plane, so it has components ax and ay, and then we'll imagine that b vector comes somewhere over here, this time still in the xy plane but over in the negative x direction. So that's the vector b. They'll project that back to the y-axis here, and then over to the x-axis here. So I have my bx, which is actually negative. Bx and by here. So now I have these two vectors a and b, and there's an angle between them here. Call it theta again. So the cross product, it calculates a vector that's perpendicular to both of these, and its magnitude depends on the magnitude of these two vectors. So if I use a right-hand rule, so I put my fingers in the direction of the first vector a and curl them towards b, that tells me that the direction of the a cross b vector will be pointing up. So I'll draw it that way. Black here. So this vector pointing up is going to be a cross b. And this is sort of the opposite of a cross product in some sense, so, or the opposite of a dot product. So we start with a cross b. And now, rather than taking the cosine of the angle between them, we're going to look at the sine of the angle between them. So we're going to have magnitude of A times magnitude of B times the sine of the angle between them. And its direction is going to be, we'll call it n, which is a unit vector that points in the direction normal to both of the original vectors, a and b, and in the direction that's given by a right-hand rule, starting from a curling to b, and then the thumb points in the direction of the unit vector. So we can write that out again using algebraic notation. So how do we actually determine what is the direction of n? I guess that's the question. So write this out algebraically. So we're going to have ax, ay, az, and then bx, by, bz. Put in my unit vectors, I, j, and k. So now to understand how this multiplication is going to work out, we have to look again at what are the angles between the unit vectors, I, j, and k. So again, the angles between them are all 90 degrees. Let's say between I and J, J and K and I, the angle is 90 degrees. But the angle between a vector and itself is 0. So when theta is 90, sine is 0, right? And when theta is 90, sine is 1, and when theta is 0, sine is 0. So it's sort of the opposite of the cosine function. So now I know that I cross J is going to be equal to K, actually. So you can work that out. If you take your hand and put your fingers along the direction of I, curl them towards J, see that that's going to point up in the Z direction, which is exactly the direction of K. And since those are both unit vectors with lengths of 1, when I multiply 1 times sine of 90, the result is just 1, and so my unit vector in that direction is just the K vector. And the same thing happens if I go J cross K, K cross I. Just gives me back whatever the third vector is. So K cross I is J, J cross K is I cross J is K. And if we go in the opposite direction, so this is sort of an I, J, K, the order of these is always I, J, K, I, J, K. So it's the same order each time. I'm just shifting them along by 1. If I flip the order of them, so now if I go J cross I, so I curl now from J to I, my thumb is going to point down in the negative Z direction. So I can say J cross I is negative K. So this is not related to the previous operation. So I'll just kind of put a box around it. And the same is going to be true if I go K cross J, or if I go I cross K. It's going to be the negative of the third vector. At the same time, if I cross any vector, any unit vector with itself, I cross I, J cross J, or K cross K, all of those are going to be equal to the 0 vector. So that's just the vector where all the components are 0. If we work that through for this multiplication, so if we expand these brackets using the cross product operation, so now we're going to have scalars and each of them multiplied by vectors. So we've reduced this operation to understanding what are the cross products between the unit vectors. So if you expand all of that out, we'll look at what each of the components are. So this is going to be the x component in the I direction, the j component, or the y component in the j direction, and the z component in the k direction. So in each of these there's going to be a subtraction. So in the I direction, or in the x direction, we're going to be looking at the y and z components. So we're going to have in here ay and az, bz, and by. So it's ay bz minus az by. Similarly, in the y direction, we're going to have the z and x components. So we're going to have the az and the bx and ax bz. And then in the third direction, the z direction, we'll have the x and y components. So we'll have ax, ay, by, and bz. If you're familiar with determinants, there's from linear algebra, there's another way of defining this to make it easier to remember. It's the way I remember it. So I'll write it as a determinant. So I'll write my I, j, and k along the top row of the determinant. In the second row, I'm going to put the components of a, ax, ay, az. And then in the third row, I'm going to put the components of b. So bx, by, and bz. This is, I think, for me at least, this is the easiest way to remember it. So if you're familiar with how a determinant works, then you're just going to expand the determinant across the top row. And you can prove it yourself by expanding this determinant that it results in this expression here. So we'll leave it there for vector products, and then in the final of this series about sort of intro to vectors, we'll look at some vector triple product relationships and how we can use those in geophysics.